Okay, guys, hi. I want to talk a little bit about atoms and isotopes and how to draw all of them. So let's go through that. This is a table, periodic table of elements. You have all the elements, most of them in here. We're going to focus on drawing atoms, and I just want to show you a really good method for you to do it. So I encourage you to do that at home because you will have to work on that on the exams and all. So if you take a nucleus, the nucleus, we just draw it this way with number of protons and number of neutrons here. And then we're going to make the first electron shell as such. It doesn't have to be perfect circle. The second electron shell and the third electron shell. I like to do it this way. Then you put the vacancies. You have two on the first one, and you put the two vacancies next to each other. You have 8 on the second one, and you have 8 on the third one. And you see how those vacancies are empty circles, right? And how they're placed at cardinal positions. And then if you work on the carbon atom, so you have the carbon atom here, so it's C, and it's 6, the number. And then here the atomic mass, the atomic weight is 12.0012. So what you would know is 6 is the atomic number, so that's the number of protons and neutrons. 6 neutrons that don't have a charge, protons have a positive charge, and electrons, 6 of them. And the way you fill the electron is starting from the lowest shell, and you fill one by one in a clockwise manner. 1, 2, and then I will start 3, 4. Do I do that? No. That's one of the things you want to be sure you don't do, is you want to make sure you fill one of each pair before you switch to the next pair. And so 1, 2, so we have 1, 2, 3, 4, 5, 6 clockwise, remember? And so now that you have all those 6 electrons placed, you realize that you have vacancies at those 4 cardinal points, which is why when you have carbon mixing with hydrogen, you have 4 atoms of hydrogen, because hydrogen here has only 1 proton, 1 neutron, and 1 electron. So if you can imagine hydrogen, it has a vacancy on the first shell. And when those vacancies merge, you see that molecule being formed. Okay, now with that, that's really what you want to keep doing. Draw the vacancies and then start filling. Carbon is 6, 12, right? And if you do oxygen, it will be a different atomic weight, but it's 8, and you can find it here, 8. And so you would do 1, 2, 3, 4, 5, 6, 7, 8. Continue clockwise, and now you see the two vacancies are here. And that's what creates that imbalance that's so important for the rest of the lesson. So, because the two vacancies are next to each other and not opposite to each other, so it's really important to fill in clockwise because it's how it works. So another thing I want to talk about, the isotopes. So remember, like the atomic weight is something like that for hydrogen and oxygen. For carbon, it was 6 and 12.012. So the isotopes is the different variations that exist out there. Of course, for oxygen, it would be 8 and 8 here. So if we focus on oxygen, if you have 8 protons, 8 neutrons, knowing that neutral charge, positive charge, negative charge electrons, right? The electrons don't have a mass. That's mass of 1, mass of 1. That should be 16. If all oxygen had 8 protons, 8 neutrons, and an electron, it would be 16 the atomic weight. However, the weight is a little bit lower, which means that out of all the oxygen out there, maybe 99% is like that. And 1% has 8 protons, but only 7 neutrons. Same number of electrons, same number of protons, the charge doesn't change, but the neutron is 7, so now it's 15. 8 and 7, 15 instead of 16. And if you do the average of 99% being 8, 8 and 1% being 8, 7, you get something really slightly lower than 16. So for carbon, since it's slightly above 12, which would be 6 and 6, 6 protons, 6 neutrons should be 12, since it's slightly above 12, that means that 99% of the carbon is like that, whereas 1% of the carbon is 6 protons and 5 neutrons. Sorry. See, it's slightly above 12, so it's 7 neutrons. It's slightly heavier, has one more neutrons. What does that mean? That means instead you have heard of a carbon 12, 13, carbon 14. So it means that you have even a smaller portion. Maybe this is 98, and you have another percent that is 6, 8, which will make 14 total. So carbon 14 is simply atoms of carbons that instead of having 6 protons, 6 neutrons, 6 protons, 8 neutrons. That makes them unstable, which we can use it for datation. So you can look up how datation works, but it's simply that those 1% don't really stay stable and tend to lose their neutrons to go back to carbon 6, 6, so carbon 12. But ultimately, you also have a formation of carbon 14s regularly, and it's due to a lot of factors, including the sun. It's not for this lesson, but now I want to talk about remaining charges. So what do I mean by remaining charges? Here in this PowerPoint slide, you can see the one atom of carbon, as I explained, 6 protons, 6 neutrons, 2, 3, 4, 5, 6, right? And you had 4 atoms of hydrogen, it's 1 proton, 1 neutron, actually no neutrons, 1 electron, and a vacancy. And they merge this way, as we talked about, all the cardinal points. So what's happening here, and I'm going to make a diagram that's simplified of carbon and hydrogen here. And usually that's methane, by the way, molecule of methane, and we represent those links as such with a bar. You've probably seen it in chemistry. What I want you to visualize is the electron. So we're going to obviously not be concerned with the 2 electrons that are just orbiting around carbon all the time. But now it should have 4 more electrons orbiting around carbon. But those electrons also orbit around each hydrogen. The reason why it's showed like that and it makes a covalent bond is because that electron path, those 2 here tend to do this, always around carbon. Now the electrons that are shared between that hydrogen and that carbon tends to do that. That electron tends to do this and spend as much time around the hydrogen as around the carbon. And so both of them are sharing, which then, because there's only 1 proton here in that nucleus, right, and there are 6 here, that means that that electron tends to spend more time there rather than here, that electron. Why is that? And I shouldn't use pluses because it's going to be confusing. It's an electron. So why is that? It's because you have 6 positive charges here, 6 of them, 6 neutrons, 6 protons here, and here you have only 1 positive charge. So the electron, being negatively charged as it is, tends to be more attracted towards those 6 charges than it is than 1 charge. So it tends to spend more time there, which should create a remaining charge here. Why? Because now instead of having 1 proton and 1 electron fully spending its time here, that electron doesn't hang around here as much, which leads to that hydrogen to be a little bit more positively charged. And remember that symbol here that we'll talk about in a second for the hydrogen charge. That should be a remaining positive charge because there's less of the electron doesn't spend its whole time here, it spends more time here. And here you will have a remaining negative charge due to that. Because now instead of having the 6 electrons going around it, it has a 7th one that is shared. Remember, the 7th one comes from the hydrogen, spending more time here. So you should have a remaining negative charge here. But it's not the case in the case of methane because those remaining charges are opposed by the same here, the exact same here. So the tug that happens between those 2 is also happening here, and here. And since you pull in the forward direction, everything is fine. Everything is just as you used to see, like that. And that's just because the tug is opposed on cardinal points, right? And now, if we take a look at, we're going to skip that example because the 2 oxygen together, same thing, the tug is putting the direction opposite to each other. But now if you look at oxygen and hydrogen or water, so if you draw water, which it would be an oxygen here, H here, and an H here. Now you have, once again, a little bit different, but you have 8 protons here, right? So positive charges. You have only 1 proton here, so a positive charge. And you have only 1 proton here, so a positive charge. And now what you see is the same thing, that electron that is shared. So you see here, oxygen has 2 that stand around it, and then those 2 spend all the time here, those 2 spend all the time around oxygen, but that one and that one from oxygen usually spend all the time around oxygen, but now it's merged with another one, because you remember the vacancies here are met with the vacancies of hydrogen. So now those 2 electrons here that are orbiting between oxygen and hydrogen, they are more attracted towards those 8 positive charges than that 1 positive charge, right? So it spends more time around here, those 2 electrons, than it does around there. So it spends more time here than there, which leads to remaining charges, as we just mentioned. So the remaining charge here, because the electrons spend less time here than there, that will be a remaining charge that is positive, because now you have 1 proton that's opposed by half an electron, maybe. Whereas here you have 8 protons that now don't have only 8, but now 1 more, so 9 electrons, and now you have a remaining negative charge here, right? Same thing over there, remaining positive charge, remaining negative charge. In the case of methane, as we talked before, those charges were opposed right away by an opposite hydrogen atom, and it's not the case here at all. Here there's no opposite hydrogen due to the absence of vacancies here. And that creates those remaining charges that would be extremely important for hydrogen bonding. So it's all because the nuclei of each of those atoms, the nucleus of each of those atoms, are of different proton numbers. And the higher the proton number, the more the attraction towards negative charges. So although those electrons are shared, it's not completely stolen, but it's spending more of its time around oxygen than it spends around hydrogen. Now, last but not least, let's talk about ionic charges, ionic bonds. So if I'm going to put myself right there, let's increase that and talk about ionic bonds. That video is a little bit longer than usual, but it's extremely important for us to get that straight. So here it's sodium chloride. So sodium chloride is Na. Let's start with Na. And Cl. So if you draw those, you know that Na and Cl, and we can look at a periodic table of elements really quickly. So let's see. And A here 11, and Cl over there 17. Let's find that ionic bonding again. Okay. So Na is 11 and Cl is 17. So if I make Na, they will have 11 positive charges. Just going to write Na on top over there. So it will be 11 positive charges, 11 protons, Cl 17 protons, right? So now what's happening to the electrons in those cases? If you focus on the electrons, Na will have 2 on the first, and I'm going a little bit faster than I used in the past, but you are welcome to make the valency, the shells around in dotted lines, and then making the empty vacancies and then fill them in one by one. But 11, I'm doing it at once. I'm still going to go clockwise. 2, 3, 4, 5, 6, 7, 8, 9, 10, and we're going to put that one here just to face the chlor, the atom of chlor. You see now the 11th one on the third vacancy is alone on the third shell. So I'm going to put the dotted line to help us visualize that. That guy is alone and there's an empty vacancy next to it. And it's right there. You can maybe not see it clearly, but that's why I drew it. Now 17, you have 1, 2 on the first vacancy, on the first shell. 3, 4. Oh, see, did it wrong. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Jesus, did it wrong again. 2 and 8, 10, 11, 12, 13, 14, 15, 16, 17. Empty vacancy. Empty vacancy right there on the third shell. So when those two atoms get together, it's a real party. Why? Because that atom of chlor compared to that atom of sodium has 17 protons, way more attractive to electrons. So when those two get together, they don't share nicely. Oh, no. Mind you, the chlor atom is totally stealing the electrons of the sodium. Totally, stole it completely. Boom, gone. Because 11 to 17, so far apart that those 17 protons attract way more than that 11. So you may say, oh wait, we just talked about oxygen and hydrogen, and it was 8 for oxygen, 1 for hydrogen, it's a difference of 7, and here it's a difference of 6. That's why you use the electronegativity table that's right there to think about differences, right? And it needs to be a huge difference to create ionic bond. We can talk to a chemist to see exactly how much of a difference you need to have, but that's not the point here. What I want you to know is that chlor is totally stealing the electron from Na, and Na is left, as you can see here, with only 10 electrons, which makes for a remaining positive charge of Na, and not just a full positive charge for Na, and a full negative charge for chlorine, because chlor now has 17 protons but 18 electrons, and Na has 11 protons and 10 electrons. It's been stolen, and that's why you have ionic bond that links those two. Now they're not attached by sharing electrons, simply that positive charge attracts that negative charge and they stay together. And that's it. That's really it. Okay, I'll see you guys next time.